All right, welcome. I hope you're all doing well out there. Um, so today we're going to talk about conventional and Klein milling. So this has to do with the relative motion of the cutter. In this example, we're going to use an end mill and the direction that the end mill is traveling with respect to the material. So I'll draw the material here in blue. And we'll switch to yellow here. This is going to be our tool coming along. And we'll go back to blue. So the tool is traveling up, and the material that it's cut is like that. So picture that being a perfect square block. And so the tool has teeth. And so these teeth are kind of look like this. This will be a four-fluted end mill. And so you can kind of picture we're looking through the tool and you can see the teeth and the material. This would be the top surface of the material. So the tool would be rotating clockwise and it's moving in this direction, in the upward motion. So what you'll see in conventional milling is the cut that it's going to take is going to look like that. And so it starts out with a rubbing action with cutting almost no material and progressively getting larger and larger and larger. And at the end here, this is what we call our feed per tooth. So if you order a tool, a cutter, it'll come with its own parameters of how much you can take off per tooth. So it's for end mills, it's in the range of a couple of maybe 5/1000ths of an inch per tooth. All right. So what you'll see with this sort of cutting action here is you'll see that the tool enters with a rubbing action. So when things rub, the heat goes up due to friction. And when things heat up and rub as well, the wear increases. So this would be increased wear on the tool. So this is kind of a negative, I guess, characteristic of conventional milling. And what this causes is the surface finish to look poor. So it'll be rough. It'll have wear marks. May even see it just won't be smooth or it won't be luster. You won't get that luster that you get with Klein milling. So so the surface finish is poor, and so you'll also you see as it enters the material, it's almost cutting nothing at all, and then it increases. Well, that means that your chip load is going to increase through the cut. So as this tooth cuts the material, the load increases on the tooth. And as it's cutting, it's heating up, and you're causing and your you're causing strain and deflection within the material, and that causes it to strain harden. And that also, so you get a work hardening zone. And that increases. And so all of these characteristics, such as heat, wear, chip load, your work hardening zone, causes the tool life, excuse me, to decrease. So the 2 points I want you to take away from this is that because of the heat and the wear, our surface finish is poor. So this surface finish here would be poor. And our tool life decreases. And that's due to the wear increase by the rubbing action and the work hardening zone increasing as the cut goes through. So we'll go to climb milling now, and we'll see how that differs from conventional milling. So again, we have our part here that we're cutting. And as it's cutting, we'll draw our cutter here. And so this is the material that's been already cut away. We'll go back and we'll draw our teeth on here. So there's 2 teeth there, and then it's a 4-tooth end mill. So what you'll see here when the tooth enters the material, it actually enters from this surface here. And the chip will look like this. So very much the same shape as conventional milling. And again, this is our feed per tooth. But the way that the tooth enters the material is completely different. So you actually start by taking a bite out of the material here, and the chip gets progressively smaller as the tool moves forward. So tool is moving forward, and again, it's still rotating in the same clockwise fashion as conventional milling. And the only thing that we've changed is that the tool is on the other side of the material. So let's write down the key characteristics of climb milling. So instead of entering it with a rubbing action, the tool enters by taking a bite out of the material. So that causes the tool to get a nice precise cut, and there's not as much heat generated from this, and there's not as much wear generated from this. And the heat is not, it doesn't build up because there's no sort of rubbing action that occurs while the cut is taking place. And this causes little wear on the tool. Some wear. There's always going to be a bit of wear, but not as much as conventional milling. So this causes our surface finish to be much better. So our surface finish goes up. It's smoother, more consistent, less rough, things like that. So as the tool or the tooth cuts the material, the chip load actually decreases. And you virtually do not create a work hardening zone. Or if you do, it's on a much smaller dimensional, smaller part of the chip. So the work hardening goes down. And all of that increases the tool life. So again, we'll take away things. Surface finish goes up, and our tool life goes up. So if you were going to climb mill this portion of the block, like on this side here, you would have to go in this direction rather than going up. All right, so you may ask yourself, well, why would we ever conventional mill if climb milling is so much better? The reason for that is somewhat historical. So conventional mills, which are the older manual mills that you see, they are only able to really mill by using conventional milling, hence the name conventional mill. And that's due to how the machine actually is built and how like the internal components work. If you try to climb mill with a conventional mill, you'll end up with a lot of chatter and you will get a very poor surface finish. And you can cause wear and tear on the machine and the tool due to that chattering. So it's generally something that's not done on a conventional mill. But there's another reason why you would choose the conventional mill. Let's say if you were using a CNC machine. So CNC machines are generally you generally climb mill on a CNC mill. So maybe I'll add that as well here. So maybe switch to white here. So CNC mill, whereas this one would be done on a conventional mill. So there is a justifiable reason why you would use conventional milling even on a CNC mill. Let's say you have a part that has a very hard surface. So here's a same sort of part here. And you have the tool here. And this would be moving forward like that and always rotating clockwise. So let's say this material had a very hard scaled surface on here. So why conventional milling is better in this application is because you're actually cutting through the virgin material, as they'll call it. And that causes less tool wear on the part than cutting and taking a bite out of this scaled surface. So even though you're increasing the work hardening through the chip, it's less hard than this material, so that'll increase your tool life. So that's one reason why you would use conventional milling. And then another reason is somewhat an inevitability. So let's say you were to pocket some sort of feature out of this material. And you have a tool here coming in. So as you go around, and let's say that this portion here is the part that you want to keep. So you want a nice finish on here, so you would climb mill. So as you go around, you would have to go in this direction. You would create another surface here with the tool. And so this side would be climb milled, but this side here would be conventional milled. At least until you milled all of this out as well. So it's somewhat of an inevitability that you would end up conventional milling the sacrificed material, um, and so that will decrease the tool life in pocketing than, let's say, just going around the edge of the material. So you're kind of doing both in this scenario. You're climb milling on this side and conventional milling on this side. So that's all I have for the climb milling versus conventional milling for today. I hope you enjoyed, and we'll see you in the next video.